Introduce for our next lecture Dr. Biao Lian. Dr. Lian is a postdoctoral fellow at the Princeton Center for Theoretical Science here, and he will be talking about fragile topological aspects of twisted bilayer graphene. Dr. Lian.
Okay. Great. Thanks a lot. Thanks a lot for the introduction and the invitation for me to speak here. I'm local here, so this is just an easy talk. So I'm going to talk about a relatively new concept, fragile topology, which is actually present in the twisted bilayer graphene, and I'll talk about its effect in this twisted bilayer graphene and some other systems. So I'll introduce some basic concepts, but also covering some works I did with my collaborators, Fang Xie, Zhida Song, and Andrew Berwick. So in the first part, I'll just briefly review the conventional topological states matter, which I'll call a stable topology. And then I'll talk about the concept of fragile topology. And then, in particular, I'll mention the fragile topology in twisted bilayer graphene and their effects. And I'll tell about that the topological effects of this fragile topology. In particular, these two are two of our studies. One showing there's an effect in Hofstadter Butterfly, and the other showing there's some effect in the superconductivity, enhancing the superconductivity. Okay, let me just start with the very basic thing. Although you may already know this. So the topology, mathematically, topology is describing some invariant properties of some object that is invariant under continuous deformation. And the most, one of the most simplest example is the Euler number of two-dimensional closed surfaces. You can do continuous deformations to all these closed two-dimensional surfaces, and you will always find that it can be categorized by the number of holes on these surfaces, which are called genus. And mathematically, this can be obtained by the integration of the curvature of this two-dimensional surface. So although this curvature is not invariant, it's curvature at each point is a geometric quantity. But the integration of this curvature gives you an integer number, which is called the Euler number. So this is a very simple example mathematically, but in condensed matter physics and also actually also in higher energy physics, people discuss topological theories and topological states of matter, which is basically saying that some ground states with some properties that is invariant under adiabatic variations of the system parameters, and the most classical example is the quantum Hall effect. Basically, if you measure the Hall conductance of the system at low temperatures, you find the Hall conductance is quantized in units of E squared over H, and this nu is either an integer or a fraction rational number. This property is invariant under small variations of electron fillings or disorders. So in this sense, it's the same as the mathematical concept of topology. There's something invariant under this deformations. There are many ways of discussing topological states matter, but for weakly interacting topological states, usually the topology can be characterized by the band theories. So in weak interacting cases, you always have the concept of the electron bands. So in this case, you can usually define the topological index in terms of the properties of this electron bands. For example, the integer quantum Hall effect is such a state where there are lambda levels, and also later people discuss chain insulators. So the lambda levels or the chain insulators, they all have bands, electron bands. So this is a well-known to be characterized by the Chen number, which is basically the integration of this barrier curvature in the Berlin zone. And barrier curvature here is defined in terms of the wave functions of that band. So it behaves as a gauge field. So and this integration gives you an integer, and the Hawk inductance we mentioned previously indeed is related to Chen number. It's given by the summation of Chen numbers below the Fermi surface. So so now I just talk about what is I call a stable topology, which is also what people mean previously before the word fragile occurs. So stable topology basically means first you need to have some properties that is invariant under deformations, some continuous deformations, but also it requires a stronger condition that is this topological state is stable against adding trivial state to it. So in in weak interacting cases, this can be understood as suppose you have these band structures which have some topological index. Yeah, this is a Fermi energy. For example, these valence bands have some topological index. Then you can add any trivial bands to it. And these trivial bands can also interact with the existing bands, and the topological index would remain robust. So so this is a what I call a stable topology, because it's not only stable against continuous deformations, but also you can add these trivial states to it. So here the definition of trivial state or trivial band is it can be adiabatically connected to the so-called atomic limit. Atomic limit is basically assuming you have a lattice of atoms with orbitals that are decoupled from each other. So in this case, this band, a trivial band, will have local one-year orbitals, and in the atomic limit, you can tune them to zero hopping. So this will just be a trivial flat band. So basically, this means you can add this trivial band and turn on any allowed hoppings, and this topological index should remain. So for example, a trivial band, you can prove it's always Chen number 0. So the Chen number is actually a stable topological index. So stable topology can also be generalized to when you have symmetries. So in this case, you just require that all the trivial states or any one-year orbitals you consider have the symmetries you added. So in this case, yeah, again, stable topology is stable against adding trivial bands, and trivial bands here is defined as local one-year functions decoupled with each other, but at the same time they respect the symmetries. So for example, you can consider adding a time-Rosso symmetry, and in this case, the time-Rosso symmetry restricts you to that any bands to be doubly any one-year orbitals you added to be time-Rosso invariant. For example, if you add angular momentum non-zero bands, it has to be plus minus j, or if you add a angular momentum 0 band, it can be a single band. So this leads to the well-known concept of topological insulator, which Professor Fu also discussed a lot. So I just quickly go through. So yeah, so for the Chen insulator, we already see that the topological index is just the Chen number, which is an integer. For time-Rosso invariant topological insulator, the index is a Z2 index. So there's only one kind of non-trivial state. So in particular for inversion symmetric topological insulators, actually this time-Rosso and the inversion together protects a twofold degenerate, protects your bands to be all twofold degenerate. And then in this case, this Z2 topological index is simply given by the product of the parity eigenvalues of the time-Rosso invariant momenta. So here I just draw a simplest example, which have 4 bands. You have twofold degenerate bands here and here. And for example, in this case, if you have parity minus here and plus in all the other high symmetry points, it will be a topological insulator. So this is I draw here as a 2-dimensional example, which is the quantum spin Hall effect. And furthermore, you can further generalize this to, you can add space group symmetries or crystalline symmetries. And this will lead to further concepts of topological states, which are topological crystalline insulators. And people also discuss topological semi-metals. So when you have space group symmetries, you can have more varieties of semi-metals as well. So again, in this case, stable, if you want to define stable topology, it has to be stable against any trio band. But in this case, you have more symmetries, and the trio band is defined again to respect all the symmetries. And to do this, actually, you need to put your if you want to create a trio band, in this case, you need to put the winding orbitals on the so-called Wyckoff positions, which are basically the high symmetry points for your lattice. Just to give you some more examples, for example, in this case, in this honeycomb lattice, the Wyckoff positions, there are three kinds of Wyckoff positions. You have these blue ones forming the honeycomb lattice, this black one forming a triangular lattice, and these red ones actually form the Kagami lattice. So yeah, in this case, for example, if you want to add this orbitals at this red position, you need to add at the three positions at the same time because they transform into each other under C3. So this will give you a three-dimensional representation, or basically you have three degrees freedom per unit side. And this is a lower symmetry case. So in this case, you just have C2 symmetry. Then you have four distinct Wyckoff positions. You can, if you want to create a trio band, you can put your orbital on either of them. Okay, so now come to the concept of fragile topology. So you might already get some sense that you can actually relax the requirement for topology. So topology is basically something invariant under continuous deformations, but stable topology also requires you to be stable, the topology to be stable upon adding trio states. But for fragile topology, it's basically defined as there is some invariant topological index for it. Basically means it cannot be decomposed. So the system cannot be decomposed into several trio systems. But in this case, if you add some additional trio bands or trio systems, this topology can be trivialized. Yeah, this might be a little bit counterintuitive, but I'll give you a simple example to see this. Yeah, so in this case, basically, you can add some trio band to a topological system, and after some deformations respecting all the symmetries you have, you can make them into some atomic limit trio bands. This is the concept of fragile topology, first introduced by Adrian and Ashwin. So this is quite recent. So yeah, to see a very simple example, let's consider a topological insulator with time reversal symmetry breaking. So in principle, if you break time reversal symmetry, the topological insulator is no longer stable in the original sense. In this case, it's called an axion insulator. But if you still have inversion symmetry, I mean, if it is an inversion symmetric TI with time reversal breaking, you can show that there is still some fragile topology in this system. So yeah, this is an illustration of the breaking of time reversal symmetry. So this is just the previous example, quantum spin Hall example I showed. You have two valence bands here and two conduction bands here. So yeah, EF is here, sorry. So if you put your EF here, your occupied bands, there are two occupied bands, and you can still define the inversion parity eigenvalues at these high symmetry points. So these points now are still in inversion symmetric, although time reversal is broken. So you find you have two bands with negative parities here, and all the other high symmetry points will have a plus parity here. Then we can think we can take a look at what trio bands a square lattice can have. So here I just assume this is a square lattice. So for a square lattice, you have 4 kinds of Wyckoff positions. So this I just show a concrete example of how to think about the trio band. Suppose you put a p orbital on this Wyckoff position 4, and so basically this is a single band. So you have 4 you have this pz orbitals at every 4 positions, and this is a flat band. So you can easily write down the wave functions in momentum space. This will just be given by this expression. So we have k is the quantum momentum, but here you need a tau 4, which is the shift of this, which is basically characterizing the position of this 4 position. So if I define the inversion center of this lattice as position 1, this 4 will be reflected to this position here. So by looking at this wave function, you can actually find the inversion eigenvalues of this band. For example, yeah, if you look at gamma point is pretty straightforward. You have k equals 0, and so basically at every side, every 4 sides, you just get an amplitude 1. So this is inversion symmetric, but the p orbital itself has a negative parity, so it's a negative sign here. If you look at this m point, maybe let's look at this x point. If you look at this x point, so here you will get basically if you look at this wave function, here you get a factor I, and here you will get a factor minus I. So under inversion, there's a minus sign here, and plus the original minus sign of the orbital itself, you get a plus sign here. So in this way, you can basically tell all these. You can put your orbitals on various kind of positions. You can look at what kind of trio bands you can have and what eigenvalues they can have. So these eigenvalues basically is the simplest example of the so-called elementary band representation. Basically is the representation of the trio bands. Here are just a list all kinds of four positions. And the trio bands at all these 4 positions can have these. If you look at the eigenvalues, they behave like this. So here, eta is the parity of the original orbital you put here. So basically, the orbital itself has a parity eta, and then depending on where you put the orbital, you can have these different kinds of eigenvalues. So now let's look at this example of quantum spin Hall with time reversal breaking. You find you need 2 negative signs here and 2 plus signs at all the other positions. And if you look at back all these 4 kinds of eigenvalues, you find there's no way you can choose two of them to give you these kind of eigenvalues. So this actually proves it's a topological non-trivial state. It cannot be decomposed into trivial bands, atomic limit trivial band. But again, it's actually fragile. You can actually add a for example s orbital at this 4 position. S orbital just means your parity is plus, the intrinsic parity is plus. Then you just plug in the eigenvalues of this s orbital at 4 position, and this is the eigenvalues you can get, and you get a basically this is what you get after adding this s orbital. But if you look at back, what do we have for the trivial bands? You find these eigenvalues can be decomposed into 3 Wyckoff trivial bands at these 3 Wyckoff positions. So yeah, this demonstrates an example of fragile topology. Basically, you added a trivial band, but you ended up with 3 trivial bands after some deformations. So this just says this this topological index is topological trivial in this case by adding just one trivial band. But I want to emphasize that this is not arbitrary. If you try to add some other trivial band, it not necessarily trivializes the system. So in this sense, what trivial bands you add to it is also not arbitrary. So here I want to let you homework. So why this trivialization procedure does not work when there's a time Rosser symmetry? Because we know that if we still have this time Rosser symmetry, it has to be a strong topological index, and this cannot be trivialized. Yeah, I think you can figure this out. Okay, so now let's talk about a practical example of the twisted bilayer graphene. So yeah, actually, the fragile topology is a recent concept, but luckily soon people found an example in the recently extensively studied twisted bilayer graphene. So let me just briefly review what twisted bilayer graphene is. So basically, yeah, this is monolayer graphene, which all of you are familiar with. So at low energies, the monolayer graphene would just have two Dirac fermions at K and K prime points of the graphene Brilliant zone. And here, if you look at the Dirac fermions at these two different values, they have opposite helicities. Basically, helicities you can define it as the winding of the coefficient of this sigma x and sigma y, the effective Hamiltonian. So yeah, if it's a minus sign here, I call it plus, helicity plus 1, and the opposite, I call it minus 1. So in general, in this monolayer graphene, these two values always have opposite helicities. So a twisted bilayer graphene is basically, yeah, you just stack two of them. And as a result, if you look at the Brilliant zone of the two graphenes, they are slightly rotated from each other. And what you can see is these two Dirac fermions at the same K value, they are nearby, and actually you can show their couplings are the strongest. And you can basically ignore the hoppings between this value and that value. So yeah, so and the distance between these two values actually defines the Moiré Brilliant zone, which is the Brilliant zone of this superlattice you see from the twisted bilayer graphene. So so in this basically using this approximation, a twisted bilayer graphene actually consists of two groups of decoupled bands. One group of bands is at value k, and the other is at value k prime. So under this approximation, if you just look at one value, so before you turn on the interlayer hopping, you just have two Dirac fermions. But these two Dirac fermions, they are of this in the same value. So actually, they have the same helicity. Just to remember, we said that earlier. So so this one value bands can be characterized by the continuum model constructed by Bistreeter and McDonough. So you have these two Dirac fermions of the same helicity, so on the diagonals, and there are some interlayer hoppings. The interlayer hopping has these modulations of these vectors Q1, Q2, Q3, which is basically the period of the Moiré superlattice. So this is a periodic lattice potential, and you have Dirac fermions on the diagonals. So you can further transform this Hamiltonian and diagonalize the Hamiltonian, so then you can get a band structure. So basically, what you get is before you turn on hoppings, you just have two Dirac cones which intersect with each other. After adding these hoppings, the gaps will be opened whenever these two Dirac cones cross. So yeah, the actual picture is more complicated than this. But as a result, you get these band gaps. So for example, if you open a gap here, you get these lowest two bands, which is the band structure of this Morris superlattice. And if you look at these lowest two bands, there are some properties that are preserved. That is, these Dirac points are still there. They're protected by symmetries, which I'll talk about soon. And another feature is, remember that these two Dirac fermions have the same helicity. Basically means if you look at the effective k dot p Hamiltonian near k point and k prime point of the Morris zone of the same value they will have the same helicity. This is usually not possible for tight body model. So whatever two-band tight body model you have, you always get equal number of helicity plus and equal number of, and helicity minus. So so this is actually a non-trivial part of the lowest two bands. You have a non-zero total helicity, and this turns out to be actually a fragile topological index for the lowest two bands, if you just look at the lowest two bands. So in this case, the twisted bilayer graphene, if you just look at one value, it has these symmetries, and this C2Z-T symmetry, so T is time reversal. So C2Z-T symmetry is actually the symmetry protecting this fragile topology, which I'll show in the following. So just to mention, just to recall that if you have a fragile topology, then that means you cannot trivialize the system into some local Wannian orbitals, and this also means basically you don't have local Wannian functions, and that means you don't have a local tight binding model for the two bands. So first let's look at this C2T symmetry. So this C2T symmetry is actually the symmetry protecting your Dirac points. Basically, so this C2 flips your momentum to minus, and time reversal also flips your time momentum to minus. So this is actually momentum is invariant under this C2ZT. But time reversal is anti-unitary, so just to remember that. So then C2ZT actually acting on your Hamiltonian will give you a Hermitian conjugate. And also there's a sigma x that is coming from C2Z, because C2Z actually flips the sublattice A and B. So this sigma here is the sublattice index, so you get an additional sigma x. So if you have this C2Z-T symmetry, then this indicates this equation, and that constrains your Hamiltonian. Your Hamiltonian has to be of this form. Basically, you cannot have a sigma z matrix. So in two dimensions, you have two momentums. So you have a chance to have both coefficients to be zero, and that's where the Dirac point is. And this is stable against the small variations of these functions fx and fy. So that's a protection to these Dirac points. But this is not yet the fragile topology, because actually both monolayer graphene, the bands of monolayer graphene and twisted bilayer graphene have C2Z-T symmetry. So that's not surprising. In both cases, there are Dirac points. So now let's look at what this fragile topology can characterize more rigorously mathematically. So to mention that, actually, in general, the fragile topology as well as strong topology, you can analyze them both in the way to examine whether they can be decomposed into elementary band representation or trivial bands, or you can examine the Wilson loop winding number of the bands of interest. So these two methods are kind of both indications of topologies. So previously, we just in the axion insulator case, I talked about EBR analysis. But now let's look at this the other index. Oh, sorry. The other index, the Wilson loop winding number. So Wilson loop is defined as follows. Basically, we can define let's consider just in general m bands. So for these m bands, and this is the wave function of the m bands, which is some rectangle matrix right here. Yeah, basically the Berry curvature. Recall the definition of Berry connection. Berry connection is basically defined as partial k of this uk or something. So if you recall the definition Wilson loop in gauge theories, that's just some integration of the gauge field on the exponent. So you can similarly borrow that concept here. If you define some paths in your Bernoulli zone, you can actually multiply all these. You can multiply all these inner products of these u's. These u's are this is from the wave functions, actually, so this inner product between two nearby u's is just basically e to the I of Berry connection. So this is exactly an analog of Wilson loop in gauge theories. So in this case, if you define a closed loop in your Bernoulli zone, you can always examine the product of this all these U matrices, which is a matrix. So this gives you a Wilson loop matrix for these M bands, and you can diagonalize this matrix. Yeah, not yet. Okay, so if you write the Wilson loop in terms of e to the I w, this w is actually a Hermitian matrix. So you can diagonalize this w matrix to get some eigenvalues. That's called Wilson loop eigenvalues. Yeah, then you can also basically sweep your loop. For example, here I define a loop along this key2 direction. You can sweep this loop across the key1 direction so that it crosses the whole Bernoulli zone, and look at how the eigenvalues change. In this way, you can define a Wilson loop winding number, which we'll see soon. So now let's look at what C2T symmetry can give you for the two-band Wilson loop, if the two bands have this C2T symmetry. So C2T basically, if you acted on this two-band Wilson loop, it basically flips the time reversal is anti-unitary, so it flips I and also flips W to W star. So if you have C2T symmetry, this means W is equal to minus W star. So this just so the only possible Hermitian W matrix is lambda times some sigma y. So in this case, this simple case, your eigenvalue is just simply plus minus lambda. It's defined modulo 2 pi because it's original on the exponent. So because it's always plus minus lambda, there's a chance that lambda can hit 0. Then the two eigenvalues will just cross with each other. So for example, this is the Wilson loop eigenvalues for the lowest two bands of twisted bilayer graphene, and you can see that the two eigenvalues do have three crossings here at 0. So because they cross, you can actually define a continuous evolution of these eigenvalues. If you look at this eigenvalue, so this K1 is the direction which you sweep the Wilson loop. So if you sweep over K1, you find this eigenvalue winds by 2 pi actually, and also the other winds in the other direction. So this is defined as the Wilson loop winding number. In this case, you have a winding number 1, which is actually characterizing the fragile topology of these two bands. If you do a similar calculation for the axion insulator they talked about earlier, you can also see a winding number 1 actually. So this is pretty general. But if you look at monolayer graphene, it will just be different. There will be no windings, and so the two eigenvalues just go directly. So this basically shows that twisted bilayer graphene and monolayer graphene are in different topological phases. But how do we see this topology as fragile? Yeah, this is actually also clear in Wilson loop picture. So yeah, this is not necessarily the actual case, but suppose you add some you add some trio bands. If you just add a trio band, because every side is decoupled, what you will get is just an additional straight line here or here. So here, in this example, I add 2 trio bands. You just add 2 straight lines here and here. But then if you turn on the couplings between them, yeah, you actually need to prove that, but here I just show the result. So then the gaps between these eigenvalues can open at non-zero positions, and then what you get is a four eigenvalues as shown here. So in this case, you don't have windings actually, because this is not going from pi to minus pi, so it's not winding. So after coming here, it will go back in another path. So in this case, your winding number becomes 0, and your system is trivialized. So this means you add some trio bands, you can trivialize this topology. And also, let's look at the symmetry protection. So if you break C2T symmetry, the Wilson loop, basically, this Wilson loop operator will no longer be a form lambda sigma y. So you can have some other matrices like sigma z or sigma x, and that will basically gap out these crossings. So what you get is, again, there's no winding again. So this basically shows this is a symmetry protected and also a fragile topology.
What about the crossing at pi? You didn't have it there.
There's no crossing at pi actually. I think. There is. Yeah. Okay. Yeah, I guess that will open.
Gapped as well?
Yeah, that will open. Let me see. Maybe that's not because I think in that case lambda is pi, then plus pi and minus pi.
Pi plus pi minus pi.
Oh yeah, they're the same. Yeah. This is just the illustration, so yeah, I should modify it. Yeah, there should be also a gap opening there.
Another question about the upper picture.
Mm-hmm.
You know, as you say, there's no winding number, but there is the feature that you have to go around twice to repeat.
Yeah.
In central bands. Is that still a topological feature? So that still has a little bit of non-triviality?
Well,
the truly trivial ones, you just go around once and repeat. Whereas this you have to go around twice.
Yeah, I'm not sure about that, but
I just wonder if that's
that's
a feature which has any significance.
Yeah, it's just not well defined. If you look at the elementary band representation analysis, it will be true. So yeah, maybe there's some.
Right, but here is a feature, and it's robust, right?
Yeah, I agree.
Does it have any consequences, or is it just... okay. Just go
ahead. That's not yet clear to me. Okay. Yeah, so we've talked about the concept of fragile topology, but one might wonder what effects it could have. So in strong topology or stable topology, it's quite clear that usually there's a boundary edge correspondence. For example, in topological insulators, quantum spin Hall, this is quantum spin Hall example again. You have protected edge states, helical edge states with opposite spins. So for topological crystalline insulators, you can also if you cut a surface which preserves the crystal symmetries, which you need to protect the topology, the edge states will still be there. You still get some gapless edge states. So for stable topology, edge states is quite a clear categorization. At the same time, in the bulk, of course, if you look at just one topological band, you can also you cannot find local linear functions. That's another feature we talked earlier. But this is not quite detectable previously, I would say. But for fragile topology, in general, there's no guarantee that you have protection of any kinds of edge states. For example, in the axion insulator case, once you break time reversal symmetry, it is known that the edge states will just be gapped out, and you can continuously deform them into the bulk states. And in this case, you won't have protected edge states. So one might wonder what topological effects this fragile topology can have. But the other feature actually remains that there's no local Wannier functions within just the bands you consider. So if there's some topological effect, it has to be related to Wannier functions. And yeah, so this is actually the general understanding for the effects I'm going to talk about. So first, actually, I'll show that this fragile topology has some effects in Hofstadter Butterfly. This is not only for fragile topology; it's also for strong topological systems. Basically, Hofstadter Butterfly is basically when you add the magnetic fields to your lattice and the flux is comparable to 1 flux per unit cell, then you will get some fractal-like bands, which are called Hofstadter Butterfly. So this is the original example by Hofstadter. You just consider a one-band model on square lattice. This is zero field band dispersion, and under field you get these Hofstadter butterflies. So at the small magnetic field, you can see these are just Landau levels from band bottom and band top, but in the middle they become fractal-like. So in this example, a clear feature you can see is that this Hofstadter butterfly is energetically bounded between band bottom and band top. And this is you can understand in this way because this band bottom always have Landau levels going upwards, and band top always have Landau levels going downward. So they basically shrink the energies, and the spectrum is bounded by the bandwidth. But this is not the case for a topological band. For example, if you consider a chain insulator, so here this is a two-band chain insulator. You have basically it's the simplest model of chain insulator. You have a band here with chain number +1, and here you have chain number -1. So this gap is non-trivial. So if you just look at this spectrum, there's nothing special in the bulk, I mean, unless you look at the edge. But if you look at the Hofstadter butterfly, just to mention, the Hofstadter butterfly are all bulk structures, bulk eigenvalues. So you don't have edge state here. But still, even in the bulk states, you can see that as the field turns on, the butterfly of the two bands are connected with each other. Or in other words, if you just look at this topological non-trivial bands, its Hofstadter butterfly is not bounded by the energy range of this band. Instead, it goes to the other bands and have a connection. So yeah, basically this is what I want to say. The topological state will have this, in general, this connection between Hofstadter butterflies of different bands. And there's a general understanding, this is not a proof, but just some understanding. Recall that as long as you have topology, no matter it's fragile or stable, it indicates you don't have local Wannier functions. But if you insist that you want to write a time binding model within just these bands, you can have non-local Wannier functions and long-range hoppings. Yeah, basically, suppose you just have one band model with these hoppings. So in general, then under magnetic fields, basically what you do is these hoppings acquires a phase given by the power substitution. So mathematically, there's a very simple theorem called Jaschgarin theorem. Basically, suppose your on-site energies are all the same, which I mean TIIs are all the same. Then the eigenvalues of this Hamiltonian will be bounded by the summation of the sum of the absolute value of the hopping matrices and the hopping amplitudes. So so if you have a short-range hopping model, no matter how the phases of this T changes, you always have a finite bound. So that's when you have a trivial band. If you have a trivial band, you have finite numbers of, or basically short-range finite numbers of hoppings. So you have a finite bound for your energies. So even if you turn on a magnetic field, you would see the Hofstadter butterfly be bounded by some energies. But if you have a topological band, in principle, if you insist to write such a model, you will need an infinite number of hoppings, basically not decaying very fast. So the summation of all these hoppings usually diverges. So you don't have this bound. And in this case, you will see that the Hofstadter butterfly is energetically unbounded. It will just go away. Because at zero magnetic field, of course, you can fine-tune the phases between all these hoppings to get a small energy band, small energy range. But when the magnetic field is turned on, in general, you get these phases, and they will just no longer be destructive. Instead, they become constructive and give you large energies. So unless the Hofstadter butterfly meets some other bands which trivializes your topology, in that case, again, together with those bands, you can construct a short-range model. So the Hofstadter butterfly might be stopped when you hit some bands that trivialize it. Yeah.
Sorry, so I have a question.
Mm-hmm.
Aren't you able to actually form non-symmetrical short-range Wyckoff functions? I mean, probably
yeah.
the mechanism doesn't.
Yeah, I mean, yeah, that's a possibility. Yeah, you mean in some cases. Yeah, so yeah, I guess that's not answered yet. Yeah, that's a good question. So in principle, if you choose some symmetry broken linear functions, you could have some you could have some short range model. Actually, at first, I'm not sure whether that's always doable. Sometimes, even if you have non-symmetric linear functions, you still need some long-range hoppings. Yeah. So the other point is this is just the argument. So the proof so far is not clear yet. So yeah, I would say that's not answered yet. Okay. Yeah, but at least this says that if you have some non-locality, these properties of your energies is kind of unbounded. This seems to be quite general numerically. So yeah, so here's an example of the fragile topology of the winding number 1 I talked earlier. So this is a model. This is a 4-band model aimed to characterize the fragile topology of the twisted bilayer graphene. So basically, you can add two additional bands here. So altogether, you have 4 bands, and within these 2 bands, yeah, this is in this model within these 2 bands, you can realize either Wilson loop winding number 1 or 0. So this is a trivial phase with winding number 0. And if you turn on magnetic field, you can see the Hofstadter butterfly is well bounded by the bandways, and there's no mixing between the butterfly of them. And in this case, if you have a non-trivial winding number, you immediately see that the butterflies of the two bands are mixed together. So this is basically kind of be understood from the picture I just talked about. So this model is actually not quite realistic for twisted bilayer graphene because it's not particle symmetric. For twisted bilayer graphene, there's another model which discussed by Ashwin's group. So they add altogether 10 bands in the system. You can see that. So basically, you can add all these bands at different Wyckoff positions. And in this way, you can realize a band structure where the lowest 2 bands near 0 have a non-zero winding number. And if you turn on the magnetic field, again, what you see is the Hofstadter butterfly of the lowest 2 bands are connected with the higher bands here, basically at 1 flux per unit cell. And basically, this gap originally it's a trivial gap with chain number 0. Afterwards, it's replaced by this secret 1 gap. So if we look at the actual model of the twisted bilayer graphene, the continuum model, this is a 1-valley continuum model. You can also you can also look at the Hofstadter Butterfly. But in this case, it's a little bit different from tie binding models. For tie binding models, Hofstadter butterflies are always periodic, usually periodic. Once you have your smallest hopping loop to get 2 pi flux again, your Hofstadter butterfly completes 1 period. But for continuum model, basically this twisted bilayer graphene continuum model can be thought of as you have infinite many orbitals in one Bernoulli zone. So in this case, Hofstadter butterfly doesn't have a period. So in order to in this case, we just look at the Hofstadter butterfly from 0 flux all the way to infinite flux, just to look at the whole Hofstadter spectrum. And what we find is, yeah, it's a little bit tricky. There are different phases with respect to system parameters. For example, this is theta, the twist angle, and this is a deformation parameter. So what you can see is, so there are 3 phases, but all the 3 phases has the feature I should mention. In this large angle phase, what you see is, yeah, this is not quite clear. This is a large angle, so this is just an electron part of the band structure. So this is the lowest conduction band, and there's a symmetric lowest valence band here. So if you look at, so actually, because there's no indirect gap, it's not quite clear, but there should be a gap here. So the Hofstadter butterfly of the lowest 2 bands starts from here, but at 1 flux per unit cell, again, it's connected to higher bands, the Hofstadter butterfly of the higher bands. This is similar to the 10-band model seen here. This connection, 1 flux per unit cell. And this is if you look at Landau fans of such a band structure, such a Hofstadter butterfly, there's a feature. Basically, you can see there's a C equal to +1 gap extending all the way to higher magnetic fields. So basically, in Landau fans, people can detect the churn gaps by measurements. So basically, this will show that there's a nuclear 4 coming from the spin and value degeneracies. There will be a nuclear 4 gap which extends all the way to higher bands. Because twisted bilayer graphene has a very large unit cell, this is actually experimentally detectable. Basically, you can reach 1 flux per unit cell by, for example, for 1 degrees, it's just the 25 Tesla, which is reachable experimentally. Yeah, so then there's another phase, lambda 2, which is a little.
What's U naught on the vertical axis here?
This is the relaxation parameter, basically, yeah, saying the reduction of hopping at AA stacking. So yeah, but there's a phase lambda 2, which is a little bit tricky. If you look at any finite flux, the Hofstadter butterfly is not connected of the lowest band. So this is the lowest connection band. The Hofstadter butterfly is not connected to higher bands, but actually it's connected at infinite flux. So infinite flux actually is indeed a part of the Hofstadter butterfly, because remember that this Hofstadter butterfly of continuum model does not have a period, but you can still recover this period by identifying plus infinity and minus infinity. In this case, phi to infinity can be regarded as the half period point of the Hofstadter butterfly. Yeah, just to see that, you might notice that 0 magnetic field is C2T invariant, but infinite magnetic field is actually also C2T invariant. You can also see that in the model. So this behaves exactly like 0 point and pi point of the tie binding model Hofstadter butterfly. So in this case, the Hofstadter butterfly is still connected between the lowest band and higher band. And finally, there's this lambda 3 phase. It gets more connections. Basically, it's connected at both 1/2 flux and 1 flux. Yeah, so as I mentioned, this is if you look at Landau fans basically measure the longitudinal conductance of the sample under magnetic fields. You will see these Landau fans. So in this case, there there are two Landau fans coming out, extending to higher bands. So this is therefore an experimentally testable fragile topological effect. Okay, so now let me move to another effect, which is basically the fragile topology also helps enhancing the superconductivity under some conditions. So yeah, just to see that, let me just briefly review that. In twisted bilayer graphene, people get interested in this system because it shows superconductivity upon twisting, and this superconductivity is only seen at when you're near the magic angle. So the magic angle, I didn't mention previously, but magic angle is defined. If you look at the band structure of twisted bilayer graphene, when you're near magic angle, you would find the lowest two bands become extremely flat. So so that means this superconductivity is really happening in these very flat bands. So therefore, this is a motivation that we should consider superconductivities in flat bands. But usually in two-dimension, superconductivity is not preferred in flat bands if the bands are trivial. So just to recall that, basically we know that in two-dimension there's no long-range order. Actually, so actually two-dimensional superconductor does not have long-range order. It's not understood in the same way as three-dimensional ones. Instead, it needs to be understood in terms of the BKT transition. So the superconductivity is actually in a BKT phase. Basically, if you do a mean field calculation, of course you can get some order parameters. Yeah, you get an amplitude and also a phase factor here. So and when you consider the fluctuations in the system, this superconductor will be described by an effective XY model. Basically, these phases can fluctuate in the space, and the coefficient of this gradient phi squared is called the phase stiffness or superfluid weight. So you can calculate this ds by just doing variations with respect to gauge field A. So this F here is the free energy. So this is also basically the coefficient of the London equation, just from the definition of itself. So yeah, so it's actually also a measurable quantity. So in Ginzburg-Landau theory, if you just plug in all these auto parameters, you will find the free energy be given by this formula. So basically, this gives you a superfluid density, which is proportional to your superconducting density, but divided by the effective mass of these electrons. So so then this ds actually determines your superconductivity temperature. Basically, because in two-dimension, vortices of the superfluid vortices can arise spontaneously. So if you consider the energy of vertex, you would find its energy is proportional to log of the size. But at the same time, the entropy of this vertex is also proportional to log of the system size. So this gives you a free energy of this of one vertex to be of this form. So if temperature is too high, then this coefficient could be negative. Sorry, there should be a T here. Sorry. Yeah. Yeah. So this gives you the BKT transition. Basically, for temperatures smaller than Tc, this Tc, vertices are not preferred. So you get a kind of ordered state, but it's actually not a long-range order. It's a quasi-long-range order. But for temperature higher than Tc, vertices just proliferate, and you get no long-range order. And in that case, you just get a metal. Yeah, so in general, this Tc, the BKT temperature will be smaller than the mean field mean field superconductivity temperature. The mean field temperature is just your zero temperature pairing divided by 2 kb. So in general, superconductivity is reduced kind of in 2 dimensions by fluctuations. But recall that in Ginzburg-Landau theory, we get a ds which is inversely proportional to effective mass. So if you have a flat band, that means m star goes to infinity and your Tc just goes to 0. So in this sense, flat bands do not prefer superconductivity in 2 dimensions. So why? So assume. Of course, the twisted bilayer graphene not necessarily has that flat band, but we can ask a question: why the flat bands can have a superconductivity? So for this, if you consider trio band, there's actually a picture why the superconductivity, the phase stiffness goes to 0. Basically, if you have a trio bands, you can decouple them into local Wannian functions, and these Wannian functions. In the flat band limits, these Wannian functions just don't have hoppings in between, so they just behave as decoupled orbitals. So each orbital, of course, they can have a pairing, but the nearby side won't have a strong correlation. So that basically says this phase stiffness goes to 0. But for topological flat bands, recall that if we insist to write a type binding model or hopping model for the topological band, it will have non-local Wannian functions. So in this case, there will be overlaps between these orbitals, and the pairings on these orbitals should still have a correlation. So that's the basic expectation, that if you have a topology in the flat bands, your superfluid density can be non-zero. So indeed, if you just consider a simple model, you have a bunch of flat bands which are degenerate. So for simplicity, you just consider they're exactly flat, and they have a gap to all the other bands. And assume you first do a mean field calculation, and you get some pairing delta inside these flat bands. So here I just assume the gap to the other bands are much greater than delta 0. So in this case, you can basically project the physics onto these flat bands. So basically, this UK dagger is a projector to the flat bands. So you can consider such a pairing, and you just you can use the definition of superfluid weight to derive the superfluid weight, and as a result, you find superfluid weight has an expression like this. So here, nu is the fitting in these flat bands. And here you get an integration of the so-called Fubini-Studi metric. The Fubini-Studi metric is given by the wave functions, so it also reflects the information of the wave functions, how the evolution of these wave functions as function of k. So for trio flat bands, upon some deformations, basically. In general, you can approximate UK as independent of k. So in this case, GIG could go all the way to 0. So this just means your superfluid weight for trio flat band can go to 0. But for non-trio bands, there's actually a lower bound for this Fubini-Studi metric. This is first considered by these people also quite recently. So if you consider, for example, 2 term bands, but with opposite Chen numbers, so they can still form a time Rosso invariant pairing. If you consider such a system, you can actually find that this Fubini-Studi metric is bounded by the Berry curvature at each k point. The basic idea is you can define a positive definite matrix which has its Hermitian part given by GIG, and anti-Hermitian part given by Berry curvature. So the positive definiteness of the matrix give you this relation. So then together with the expression we have, we find this. So here the trace of your superfluid density matrix is bounded by the integration of the barrier curvature. And the integration barrier curvature in this case is non-trivial. It's the Chen number, non-zero Chen number. So this gives you a lower bound of the superfluid density. If it's an isotropic system, then trace ds is just 2 times ds in each direction. So so this shows an example. If you have a topological flat band, you should have some non-zero lower bound on your superfluid density, and as a result, you get a non-zero TC. So for for the C2T protective fragile topology, just using previously we obtained that the Wilson loop is of this form, and you can similarly show that this Fubini-Studi metric is bounded by basically the winding number of this Wilson loop operator. So this again gives you a superfluid density lower bound. So that kind of says that why even if you have a fragile a flat band, you can still have some non-zero TC due to this topological fragile topological index. This is just the estimation. So basically, you can solve the equations to determine the lower bound for your TC. Assume you have a mean field. You know the mean field delta 0. So in this case, in twisted bilayer graphene, if you assume the band is perfectly flat, and so this is for a quantum splitting, you just get a TC equal to it's of the same order as the mean field TC. So in this case, so you do get some non-trivial contributions from topology. But I need to emphasize that this topological lower bound is only playing a dominant role when your bandwidth is much smaller. It is smaller than the mean field delta 0 you get. So because if the bandwidth is large, your effective mass is not that large, and in that case, the Ginzburg-Landau contribution is comparable to it's larger and larger, and will dominate over this topological feature. So this is really working in a strong pairing case. Just to mention, so this in general, this indicates if I have a topological band, the superconducting TC can actually, in principle, can actually be much larger than the bandwidth. This is not possible if you have a trivial band. Although we have a BCS-BC crossover, basically your delta 0 can be as large as possible, but due to the phase fluctuations, your TC cannot exceed your bandwidth. But for a topological band, this shows that there's a way to go beyond your bandwidth. Okay, with this I'll just conclude my talk, and questions. Thanks.
We can see P plus IP or something like that.
You mean what's different for P plus if we have a P plus IP superconducting?
Yes. So
yeah, that's actually in general, this picture of non-local one-year function should still work. So you should still get some lower bound, but you might need to do a different calculation to show this lower bound, because here I'm just assuming a uniform pairing, because this is basically because you have no dispersions, and it seems that a uniform pairing is the most straightforward. But if you assume some other kinds of pairing and do the calculations, you should also find some lower bound. Yeah, but I mean, this picture in general is kind of the understanding.
That lower bounds also would be bounded with the topology, or what's the expectation?
You mean for the P+IP? Yeah. It certainly will have some information from topology. Basically, what you see is if you calculate this ds, what you would get is some derivative of this matrix UK. In this case, it's quite neat. It's just a Fubini student metric. But in that case, you still get some derivative of UKs. And from the derivative of UKs, the information of topology will be reflected. Yeah.
If there are no more questions, let's thank the speaker one more time.